Hey everyone, this is Muhammad Nadeem and welcome to my YouTube channel. Today in this video, we will discuss the applications of Gauss Law. Gauss Law have many applications, but I consider two of them. The first application is if a large number of positive charges are arranged in the palm of sheets and someone asks you to find the electric field intensity at some distance r from that sheet, then Gauss Law help us to find it. So the first application is this electric field intensity due to an infinite parallel sheet of charges. And the second application is when someone asks you to find the electric field intensity between two parallel plates of the capacitor. So in that regard, Gauss Law help us for finding electric field between that capacitors. So the second application is electric field intensity between two oppositely charged parallel plates, such as in capacitor. So let's start the video. This is the first application of the Gauss Law that we will discuss in this video. In this application, we have a large sheet and label here as a red color, and there are large number of positive charges present on the surface of this sheet. So here is a large number of charges. So the concept of the charge density come into picture, and the charge density is actually the number of charges present per unit area, and its unit is coulomb per meter square. And if we are asked to find the electric field intensity at this point, at distance d above this sheet, in order to find the electric field intensity at this point, we have to draw the area around this point. So this is the area around that specific point, and at the same distance below this sheet, we have also to find the same area, and there is a large number of electric field lines originating from these positive charges. So from the above and below this sheet, there are large number of electric field lines comes and that are parallel to each other. So each positive charge is associated with the electric field line. So this electric field line is originating from this positive charge, and similarly the electric field line originate from this positive charge. And in this way, large number of electric field lines originating from this sheet in upward and a downward direction as well. So this is actually, we select the area, and we if we connect these two areas, this area and this area, so there will be the rod-like structure will be formed. So if I connect these two in this way, if I connect that in this way, a rod-like shape is formed around this point, and this rod-like shape above and below this sheet is called the Gaussian surface. So this is the Gaussian surface. So this is actually the blue color is actually a Gaussian surface in the form of cylinder. This is just like the pipe-like structure, and at the same length above and at the same length below of this sheet. So there are electric field lines originating from this sheet. So number of electric field lines are and will be interacting with the upper area, and also the number of electric field lines will interact with the lower area. So the flux through the upper area and the lower area and the area of this cylinder is determined by the Gauss law. According to the Gauss law, the flux is given by the charge enclosed divided by the permittivity of free space. In this case, there are large number of positive charges arranged on this sheet. So here the concept of the charge density comes into picture, and from this charge density formula, we determine the charge as Q is equal to sigma into A. So in this case, this equation become phi is equal to, instead of Q, we will write it's this value, which is actually, this is actually sigma. So sigma into A divided by permittivity of free space. Now in the left side of this equation, this is called the flux, and flux is defined as this is actually equation 1, and the flux is defined as the number of electric field lines that pass through an area. And there is a dot product between electric field lines and the area, which is equal to E A cos of theta, because this is the dot product. So this phi is equal to E A cos of theta. And this is the A is actually the electric field intensity, A is the area, and theta is the angle between the electric field intensity and the area A. So in this case, we have the area in the upper side and in the lower side of this Gaussian surface. So the direction of that area is given as the direction of the area is perpendicular to the area. So in this case, the direction of the area is in this direction from lower to upward. So this is the direction of the area. Similarly, at the lower side, the direction of the area is also in this direction. Okay, this is the direction of the area. And similarly, the flux also pass through this the walls of this cylinder. Okay, so through the area of the walls of this cylinder, the direction of the area is actually perpendicular to the area. So here in right side of this cylinder, the direction of the area is actually from left to right. The direction of the area is from left to right. This is the direction of the area for this cylinder, and similarly the direction of the area at right side of this Gaussian surface in the form of cylinder is this. Okay, so this equation now I am going to put the value of phi here. So this equation 1 become equation 1 imply that in the left side of the equation is the phi, and the phi is actually is equal to E A cos of theta, and which is equal to, instead of this I write this, and which is equal to the sigma into A divided by permittivity of free space. Now in this case, this EA and cos EA into cos theta comes from different sides. So here first here will be the EA cos theta. The flux is actually occur due to this area, and also from the lower side of this area, and the flux is also concept is also come from the around this Gaussian surface. So here we have this flux is actually come from EA cos of theta from the upper surface, from the upper area, from the upper surface of this Gaussian surface, plus this is actually plus, okay, this is plus the EA, the flux through the lower area is equal to EA cos of cos theta through the lower surface, and now the E plus the EA cos of theta through the sides of the cylinders, okay, which is equal to instead of this I'll write these all and at the right side of this equation comes it's their own place. So sigma A divided by epsilon naught. In this case, this theta is actually the angle between electric field lines and the vector of the area vector. So in the upper area, the electric field lines, the direction of electric field lines is actually from the lower sides to the upper. So this is actually from this positive side, originating from this positive sides and moving in upward direction, and the direction of the area from the upper side is also from the lower to the upper. So this is the direction of the area. So the direction of electric field line, so this is also electric field line. The direction of electric field line and the direction of the area both are in the same direction, therefore the theta between them is 0. So here I put that EA cos of 0 plus this is actually the EA cos theta from the lower side. So at the lower side the direction of the area is from the in this direction, and the direction of electric field line also at the same direction. So the angle here in the lower side is also 0. So instead of this we write that A cos of 0 plus this is actually the flux through the surface of this Gaussian in the form of cylinder. So if I consider this cylinder and the right side of this cylinder, the area of that right side is actually perpendicular to the direction of that area is perpendicular to the area. So therefore the direction is from the left to right, okay, and the direction of electric field line is from this positive to towards and the toward upward, okay. So here will be 90 angle between the area and the electric field line, and similarly at this side this is the electric field, this is the direction of the area of the Gaussian surface, and the direction of the electric field line is this. So the direction of the electric field line is from this positive to the upward. So here again is the angle is 90. So cos here I am going to write that EA cos of 90, and this is equal to, and this is the sigma A divided by epsilon naught. So this equation implies that EA cos theta A and cos of 0 is equal to 1. So plus EA cos of 0 is equal to 1. So EA plus EA cos of 90. Cos of 90 is equal to 0, and 0 multiply with this, and this total term will be 0, and which is equal to sigma into A divided by permittivity of free space. So this is one EA, this is the another EA, and this the addition of these two become 2EA is equal to sigma of A divided by permittivity of free space. So from this equation, the electric field intensity become the sigma A divided by 2A epsilon naught. So this become this A here this A is cancelled with this A, and the result become implies that E become the sigma divided by 2 epsilon naught. So this is the electric field intensity through that point. Now this is the second application of the Gauss law, which is the electric field intensity due to infinite parallel plates. These two are actually plates. This is plate A and this is plate B. This is just like a capacitor. This is the capacitor. This is actually a capacitor. This is the upper, this is one plate of the capacitor, and this is the another plate of the capacitor. I'm going to zoom this. This is the plates of the capacitor. So this upper plate of the capacitor is attached with the battery and the positive terminal of the battery. This is attached with the positive terminal of the battery, and the lower capacitor is attached with the negative terminal of the battery. Now if I on this battery, now if I on this battery, now if I on this I on this battery, the positive charges are moving toward this plate, and the negative charges from the battery is moving toward this plate. So here there will be a large number of positive charges appear on this plate, and the large number of negative charges appear on this plate. And we know that there will be electric field lines originating from this positive charge and will terminating towards the negative charge. Here in this case, the charges, the electric field line will originate from this positive charge and will terminate on this negative charge. Similarly, from this positive charge, the electric field lines will come and terminate in this negative charge, and in this way the large number of parallel electric field lines will arrange between these two plates. So that arrangement is this. Here if I click on this button, here will be the large number of electric field lines will be directed to the lower plate, because on the upper plate there are positive charges, and these electric field lines are originating from the positive charges and terminate in the negative charges. Here we have this is actually a positive, this is actually a plate, a long plate which contain large number of positive charges, just like we saw before in the case of the capacitor. So this is actually that plate which has the positive charges, and similarly in the lower side we have this plate, and which contain large number of negative charges, and the electric field lines will originate from this positive plate and terminate into this negative plate, So this is the direction from the upward toward the lower side. And we are asked to find the electric field at this point between these two plates. So in order to find the electric field intensity, we have to consider the box like shape around this point. this box is actually a Gaussian surface. This is actually a Gaussian surface. So in order to apply the Gauss law, we must have to consider a Gaussian surface around that point. At the previous case, we consider the cylinder like shape as a Gaussian surface. In this case, we consider the box like shape. So here I'm going to find the electric field line at this point, and I consider a box like shape, and this box have many faces. One face is toward us from the screen toward you, the one is from the left to the right, and the other side of the box from the left to the right, and other is from the upper side to the lower, and the other one is from is inward to the screen. So now we will apply the Gauss law on this scenario. The Gauss law is we know that Gauss law, let's say that the flux through I'm going to change this color. This is invisible, so the color I select is red. According to the Gauss law, the flux through this closed surface here I consider as a Gaussian surface, as a box. So the flux through this closed surface is equal to the charge enclosed divided by the permittivity of free space. So here is a large number of positive charges. So the concept of the charge density come into picture. So the charge density, which is represented by this sigma, is equal to the number of the charges per unit area. So from this we can determine Q is equal to sigma into sigma into Q is equal to sigma into A. So let's put the value of this Q here. So this flux become sigma into A divided by epsilon naught. And we also know that this sigma is actually this is equation 1, and this sigma is actually the number of electric field lines that pass through the area which is present at the some angle to that electric field. So phi is equal to EA cos of theta. Here in this case, the flux which is come from this positive charges, this positive plates toward this negative charge, the electric field lines which are comes from these positive charges, these positive plates towards the negative plate, and this is the area. Each surface, each side of this box is an area for through which this electric field line is passed. So here the concept of the flux come into picture. So we can write this equation 1 is, so at the left side of the equation 1 we can put instead of this phi we can put this value. So A cos of theta is equal to sigma A divided by epsilon naught. So in this case we consider a box. This EA value come from from the upper side. It do not come from the upper side because the upper side is in contact with the plate. So this flux can this EA cos theta value can come from the right side of this box, and it also can come from the left side of this box, EA cos of theta from the left side, and it also come the EA cos of theta inward to the screen, EA cos of theta inward, and EA cos of theta outward from the screen, EA cos of theta outward from the screen, plus EA cos of theta at the lower side of this box, lower area of this box. So a cos of theta at the lower side, which are equal to sigma a divided by epsilon naught. Here I write these all factors, these all side. So here I write the flux value which is contributed by the each side of this box. So now we are going to find the theta, and this theta is actually the angle between the electric field intensity, electric field line, and the area A. So here the electric field line is in this direction, from the positive plate towards the negative plate, and here the in this case this in this surface, this is actually the area. And the direction of the area is perpendicular to the surface here. Therefore the direction of the area is toward is outward from the screen, and at this side, at this side of this box, the direction of the area is toward the right side, and similarly at each side the direction of the area is perpendicular to the area. Here at first I am consider the first case. Here EA is equal to cos theta of the right side. So this is at this side I am going to find the flux. So here the angle between the electric field lines which comes from the upper side towards the lower, and the direction of this side of the box, the area of this side of the box, which is in this direction. So there is an angle 90 between them. So I can write here as EA cos of 90. Okay, now EA cos theta at the lower side. So sorry, this is at the left side. This is actually for the left side, and this is for the right side. So for the right side of the box, the area is the direction of the area is perpendicular to the area. So this is the direction of the area, and the direction of electric field line is toward the lower side. So here also the angle is 90. So it become EA cos of 90 plus I consider this side. So in this side the direction of the area is perpendicular to it, toward us, and the direction of the electric field line is toward the lower side. So here also the angle is 90. So here I am writing that EA is cos of 90. Now I consider the inward side, that side. So at that side the direction of area and the direction and the electric field line will make an angle of 90. So EA cos of 90. Now at the lower side of this box, the direction of the area is toward the lower side, and also the direction of electric field line is also towards lower. So here the angle will be 0. So I can write that EA cos of 0 which is equal to which is equal to sigma A divided by permittivity of free space. So we know that the cos 90 is equal to 0. So here this expression become 0, plus this expression also becomes 0 due to cos 90, plus this expression also 0, plus this expression also becomes 0 due to cos 90, and only the value is come from this expression, and cos 0 is equal to 1. This become EA, and this is equal sign, and this is sigma A divided by permittivity of free space. So this become E A sigma of A divided by permittivity of free space. This A is cancelled with this A, and the electric field intensity at that point is given by the sigma divided by permittivity of free space. This is the electric field intensity at this point. So this was the second application of the Gauss law, and that's it, guys. Thanks for watching.